So now we're looking at differential calculus, and the thing about what we're really looking at here is how change happens, and it's useful for all sorts of things. But in terms of statistics, what this is teaching us about is predictable change. When we get into statistics, we're talking about uncertainty, but we need to understand about the mathematics of predictable change before we can understand the mathematics of uncertainty. To understand this, you'll need to know about exponential notation, or raising to a power, basic algebra, basic binomial theorem, or how to expand two terms out that are all raised to a power, the Cartesian plane or the rectangular plane, the slope of a line using the rise over run approach. Are you okay with all of that?
Yep. Yeah. I think, well, when I say okay, I mean they recognise the terms, and there's enough in here to give it a go, John.
All right, great. So one of the people who came up with this is Isaac Newton. One of the things he was particularly interested in is gravity. So, for instance, if you throw something up into the air, we'll start with this idea, and if you were ignoring air resistance, it would form a parabola. You might throw it in that way. You might throw it straight up there. It's going to form.
But they're all parabolas. They're just different.
They're all
sizes.
parabolas. And the sort of thing that Newton was interested in was thinking about acceleration, how things are changing. So if you think about distance being a change in location, and speed being the rate of change of distance.
Yeah. Okay.
So
that's really good.
Yeah. So you can look at those on your car. You can distance. Your odometer will tell you how far you've travelled. Your speedometer will tell you how fast you're going. There's then acceleration, which is the rate of change of speed, which you can't usually measure on your car. You might say 0 to 100 in 12 seconds or whatever it is. But what's he was interested in, it's kind of a difficult concept, but what's happening to that acceleration at any particular point in time, because that itself might be changing, and how do you relate that to equations we have for things so you can calculate what it can be?
Just on that explanation you just did about travel being change, I think I find that really helpful, because otherwise it's kind of, change can be a bit amorphous, but in actual fact it's just as an example of change, travel, going from A to B at different speeds, and acceleration, that's really helpful. Yeah.
So we're interested in mathematically the way those concepts relate to each other, and in particular this kind of a difficult concept of instantaneous change. How is something changing at the moment?
Okay.
And so to think about that, well, rather than have the parabola the way it works when you throw things, keep it simpler. Say y equals x squared draws a parabola like that, which we saw when we looked at the Cartesian plane. And if we were to look at the way that parabola is changing, if we to change it over some distance, we'd kind of go, so if we start with the point 0, 0, and if x changes 3 to the right, then y changes 9. So that draws a line with a slope rise over run of 9 over 3 or 3 over 1. It's a slope of 3. That clear?
Yes.
Between those points. So the real question is, what does that look like instantaneously? And we'll talk about how to get there. But
what do you mean by instantaneous? Just suddenly, in the moment? That's what I think.
I mean, at any point. So that's the point between...
in an instant.
Yeah, that's the point between 0 and 3. What about 0 and 0.1 or 0 and 0.1 or 0, like just as almost...
The rate that's happening in that short time.
In that short time at any particular point is the key kind of concept here.
Right.
It's how's something changing in real time is our real question. In terms of the mathematics, really just to get us to the point of doing other mathematics that we can do before we can study uncertainty.
Okay.
But first of all, we just need to kind of a language and a way of getting our head around how things change in real time. So if, for instance, we looked there, well, that goes from x minus 3y9 to x is 2, y is 4. Different slope of the line that slopes backward compared to that one we had. The first thing we want to get mathematically is a formula that where we can plug in any points on that line and or any 2 points, and it'll say that's what the slope is. That's our first point. We'll then look at how to bring them closer together.
Okay.
But the first point is we're looking for a formula that will let us calculate the slope once we know what the curve is and once we know the 2 points. And the way we get at that is we look at how much we need to add to x and how much we need to add to y. Now, you know that we add the same part to the left and right sides of an equation. They don't change.
Yeah.
But in this case, we're adding something to x and then we're squaring it. So what we add to x isn't going to be the same as what we add to y, because it's going to all get squared beforehand.
Right. Okay.
So we're just going to call them delta. So we call that delta x is the amount we change x.
Is delta a common? Is that a new term? Like, is that a regularly used term?
It's a regularly used term.
Yeah.
It's the Greek letter delta, like the delta of a river, and it's regularly used for anything that's changing. People might say, "What's the delta of that? That's how much it's changing."
Right.
It's probably come from this, but it's become.
No, I've heard the term. I never knew what it meant.
What the delta is? Yeah. How much it's changing?
So it's the rate of change.
Yeah.
Okay.
It's the amount of change.
The amount of change.
The amount of change. The amount of change. So x plus some delta of x, whatever that is, it's just could be anything at this stage, all squared is going to be y plus some delta y.
Okay. Yep.
And what we want to calculate is the ratio between, or the fraction of delta y over delta x.
Yep.
We're going to, and so we're just going to do some algebra to do that, so we can work out what that fraction is, what the ratio is. So first of all, we use the binomial theorem to just expand out that x plus delta x squared. It's going to be x squared plus 2x delta x plus delta x all squared, which is, we covered that in the binomial theorem, if that's a bit hazy.
I remember that.
We're going to look how we do that. And then remember that y equals x squared, what we take, this is simultaneous equations, but what we take from one side of the equation we have to take from the other, and y is the same as x squared. So if we take y from that side, we take x squared from that side and it'll still equal.
Yep.
Now we've got delta x on its own.
So you just so go on. I'm getting excited here, John.
Getting excited? Okay.
I'll let you go on.
Now what we divide one side of, we've got to divide the other side by. If we divide both sides by delta x, we've got delta y on delta x equals, and we've done two steps here. We've actually distributed the delta x, the 1 over delta x between those two terms. So we've got delta y on delta x equals 2x delta x over delta x plus delta x all squared over delta x. Does that make sense?
Sort of following it here, yeah.
Yeah, good. And then we just do some cancelling out. That delta x cancels with that delta x. That delta x cancels with one of those delta x, so it's no longer squared. So what we've got is delta y on delta x equals 2x plus delta x.
Okay.
So that's our formula for saying for any starting x and y point on that line, and any amount of delta x and delta y, or in fact any amount of delta x will move forward, this is going to give us the ratio between delta x and delta y.
So, which is the amount of change on the y-axis and the amount of change on the x-axis.
Yeah, the rise over run of a slope between 2 points.
Yeah. I'm familiar with that.
Great. So just test that out and have a look at it. So supposing for this original point, we've said, okay, we've moved, our delta x is 3. We started with 0, 0. So our starting x was 0, our starting y was 0.
Yep.
Our delta x was 3, our delta y was 9. We plug those in. So delta x and delta y should be 2x plus delta x, which is going to be 2 times, so 9 over 3, delta y on delta x, should be 2 times 0, which is our starting x value, plus 3, which is our delta x, and we calculate that out. That is 3. 9 on 3 is 3. It works, and you can see the slope of that line is 3. Every time you move forward 1 unit, you move up 3.
You move up 3.
So that describes the slope of the line.
Yep. Oh, that was cool.
It actually works.
Yeah.
Pick another one. This one that we looked at earlier, going backwards. In this case, our starting x is minus 3. Just there. Our delta x, this is the point where the line hits it again, is actually at sort of the sloping dotted yellow line hits our curve again is at positive 2x, so it's we've moved, our delta x is 5, we've moved forward 5 units, and our delta y is negative, so we've gone backwards 5 units, and we plug those into our thing. We've got minus 5 over 5 should equal 2 times minus 3 plus 5, which is minus 1 minus 5 over 5 does equal minus 1. So that works.
Okay.
So now,
another epiphany.
So
this is how you could do computer stuff.
just to prove this is really working, we're
Yeah.
going to just keep the same line but do it backwards. Supposing we said x was our starting point, x equals 2 was our starting point, and we went backwards 5 points, or 5 units, up 5 units, delta y. We should have 5 on minus 5 equals 2 times 2 minus 5, which is minus 1, 5 on. It works, same slope of the line, calculated the other way. So this is a good, robust formula. It's working. So
which we can then go and apply to a whole lot of different contexts that have the same shape.
Exactly right. But the key thing is now, if you want to find the slope of the line, or the instantaneous change, what we're really looking for is the slope of that line at a point where it just kisses the curve and then moves on, just at one point. And so all we need to do is shrink delta x down until it just gets smaller and smaller, until eventually it disappears, heads towards 0, and we can say delta x on delta y is going to be 2x. So the slope of a line just touching that curve at any point is going to be twice whatever the x value is at that point.
So is that the
It's the instantaneous rate of change. The slope of the line just touching it.
Okay.
So we have, so we write it as this. We say the limit as delta x approaches 0. So and you kind of go, well, how can you have a fraction over 0? Well, it's not exactly 0 because delta x is shrinking, but delta y is shrinking, so that ratio is staying constant, and the ratio is always going to be twice the x value.
So is that one of those ones that never gets to 0?
That's right, but in practical terms, you can take the delta x does, because in practical terms it's just vanished, but it's vanishingly close to 0.
Yeah,
is the concept
vanishingly close to 0.
Vanishingly close to 0, so you can just ignore it for mathematical terms. Therefore, we write that we write it in this way: for y equals x squared, and we now have changed that delta to just a d. Or they used to use the lowercase delta, but it just means that's a shortcut way of saying the limit is as they approach 0, dy over dx.
Okay, so is d now replaced the triangle?
Yeah, because it's shrunk down. It's saying this is the triangle as it's approaching 0.
Oh, nice.
So we just write it, and that's called the differential, or the derivative is 2x. So what this means is that at any point on that curve, the slope of that curve will be equal to twice whatever the x value is at that point.
So if I look at any point along that curve, can use that to tell me the
slope of that line.
So
exactly. So here we have x is minus 2, and so the slope of the line, 2 times minus 2 is minus 4, and you can see that that's right. When you move forward one x value, you drop minus 4 in the y value. And so when they're both at 1 and 1, you move forward one value of y, you move down you move one value of x, you move down 2 values of y.
Okay.
When they're both at 0, y doesn't change, and so on.
So if I'm building a railway gradient going up a hill, and I want it to be this consistent all the way up the hill, could I use something like that? I could measure it at each point?
Something like that. But if you wanted to put a curve onto it and measure how that curve was changing, if you wanted to use that to start calculating more difficult things like, can my train handle that curve at that that rate, you want to get into the mathematics of that. That's the sort of thing if we...
That would be an application of it.
That'd be an application of that sort of. We're just doing building blocks here of stuff we can use more lately.
Excellent.
Thank you for watching.